Alright, hi everyone. So I unfortunately missed recitation today. Uh, Sorry if I caused like any inconvenience or anything, but yeah, it was kind of unavoidable, and my bad that I couldn't I let everyone know on such short notice. Next time if anything comes up, I'm gonna try to say it earlier, but yeah, I'm gonna just upload this video onto Piazza and upload the notes as well. And if you have any questions, you can always come to my office hours or or just email me or something. But yeah. So this week we're going to be going over predicate logic. And yeah, we have a bunch of textbook questions to go over, so we'll get started. So this says to write a negation for each statement. If you recall, the upside down and symbol means for every. So if you read this, it says, for every x in the set of real numbers, this is real numbers. If x times x plus 1 is greater than 0, then x is less than 0, or x is less than negative 1. Alright, so let's rewrite this down here. Alright, so now we want to find the negation of this. Alright, so if you recall the negation of these are the negations of conditional statements right here. So it turns from for every to this backwards e, which means at least one. That's the negation of for every, right? And then the inside stuff, like p, if p then q, becomes p and not q, right? So we'll do the same here. So the negation of this becomes there's at least one, or there exists. So we'll say there exists some x in R. The set always stays the same, where x times x plus 1 is greater than 0, and the negation of this, x is greater than 0 or x is less than negative 1, right? That's the negation of that. But if you recall De Morgan's laws, right? So using De Morgan's laws, we see that the negation of x is greater than 0 or x is less than negative 1, we just flip everything, right? So this becomes x is less than or equal to 0 and x is greater than or equal to negative 1. That's the negation of that, right? So this full negation becomes, there exists some x in the set R where x times x plus 1 greater than 0 and x is less than or equal to 0 and x is greater than or equal to negative 1, right? And then I guess we could put some parentheses around this, but yeah, this right here is your answer. Oh shoot, I'll probably change the color. Yeah, That's your answer for that question. Alright, next. It says for all integers a, b, and c, if a minus b is even and b minus c is even, then a minus c is even, right? And we want to find the negation of this. So I guess we could just rewrite this, right? A minus b is even. No, there's an and here. B minus c is even. A minus c is even. Probably need another page for this. Okay, here. Right, so now we want to find the negation. So just as before, the negation of this will start with grab another color. Okay, so there exists integers a, b, c. A, b, c. And then the inside, like p, if p then q is p and not q. So we'll have p, which is a minus b and b minus c are even. So that's p, and not q, which is a minus c is even. So this is q, right? And we're just doing not q right here. So if we just rewrite this again, you could keep it like that actually, but if you want to, you could just say it clearer, like a minus b and b minus c are even, and a minus c is odd. You could just do that, because the negation of even is odd, right? So yeah, that should be your answer. Yeah. Alright, oops. Wait, I forgot to I forgot to write the there exists part, so let me do that again. So there exists integers a, b, c such that a minus b and b minus c are even, and a minus c is odd. Right, so that's your actual answer. On to the next. Shoot, why do I have this? Alright, 39. Alright, so we're gonna have to rail this in if-then form. So this says, earning a grade C minus in this course is a sufficient condition for it to count towards graduation. As you can see here, like if for every x, if px is a sufficient condition for qx, that just translates to if p then q. So we could rewrite this pretty easily. We could just say something like, if you earn a, actually no, not don't say if you, say if a person earns a grade of C minus in this course, then it will count towards graduation. That's it. Yeah, for sufficient condition, it's pretty straightforward. Alright, next. Being on time is a necessary condition for keeping this job. What is necessary condition, right? So if for every x, p of x is a necessary condition for q of x, means for every x, if not px, then not qx. Or we could just say if qx, then px, right? So I guess I'll give you both answers. So we could say this, break this into, right? So look for where necessary condition is and then break this into parts, right? So whatever's before necessary condition, we'll call this P. Whatever's after, we'll call this Q, right? So if P of x is a necessary condition for Q of x, right? We could just rewrite this to if Q, then P of x. So we'll say if a person wants to keep this job, then they must be on time. That's if Q, then P of x. Right? So that's one answer. And then another way you could say if not P, then not Q. So we could say something like if a person is not on time, then there's some, it says each day, right? Each day, then they will not keep this job. Right, so that's the negation. These are both equivalent statements. You could say either or. They're both correct. Right. Alright, on to the next. Okay. Alright, so use the facts that the negation of an and of a for every statement is a there exists statement, and the negation of an if then statement is an and statement. Rewrite the statements 43 to 46 without using the word necessary sufficient. Okay. So being divisible by 8 is not a necessary condition for being divisible by 4. So first, let's just write this, let's see what a necessary is again, right? So necessary means if not P of x, then not Q of x, right? But then it says it is not a necessary condition. So what does that mean? We have to negate this whole thing, right? Yeah, we're gonna have to negate this whole thing. So if you recall, the negation of a conditional would be, I set it up here, yeah. You connect the terms with an and you negate the second term. So we'll come over here and we'll say P of x stays the same. We no longer have the arrow, but we have the and a logical connector. And then we negate not Q of x. What's the negation of a negation? It's just Q of x. right? So this is what we want. Yeah, so that's what we want right here. So if we look at this, right, and say that this is P and this is Q, we could rewrite this into saying if a number, put this in a different color, if a number is not divisible by 8, then, there's no if, my bad. So we say a number, or no, there is a number that is not divisible by 8 and is divisible by 4. Alright, so that's your answer. But I forgot what I was gonna say. Alright, so for this necessary thing, so necessary can be broken into if P of X, then not Q of X. But it can also be Q of X, then P of X, right? Just like the question before. I took this route, but you can also take this route and you'll get a equally correct answer. Yeah. Okay, next question. Having a large income is not a sufficient condition for a person to be happy. So if you remember, sufficient condition is pretty straightforward because it just means if P of X and Q of X, right? So we could just say this is P, this is Q, and then we'll say, well, first we'll find the negation of a sufficient condition. Sufficient condition means if P then Q, right? So if we negate this is equal to P and not Q. So if you want to write this out, we'll say there is a person who has a large income and is not happy. Right? If P and not Q. Yeah, that's your answer for that. On to 3.3. Okay, so it defines two sets D and E which are equal to each other, where D contains D and E. Both contain the following elements. And we want to write negations for each of the statements, the following statements, and determine which one is true, the statement or its negation. So we'll start with A. Alright, so it says for every X in D, there's some Y in E such that X plus Y equals 1. So when it comes to infinite and non-infinite sets, right now we have a non-infinite set. For non-infinite sets, you can use the method of exhaustion, which means we try every possible scenario because there's only a finite number of numbers. Then we could try every scenario and see if even one of them misses. Since it says for every, even if one of them misses and one of them is false, that means the statement is false, right? So since we only have 5 numbers, we could try every possibility and see if it works. So we'll say for every x in D, right? So let's just say x equals -2 right now, right? And then there exists some y in E, and remember E is the same as this, such that x plus y equals 1. Is there anything in this set such that -2 plus y equals 1? Y would have to be 3. We don't have a 3 in here. So that automatically, well, let me not erase that actually. So 3 is not an element of E, so this is false, right? We already know this is false, but let's get its negation, right? Its negation would be let me just write this again. There exists some x in D. For every y in E, right? We're just negating these two things right here. This is negation of multiply quantified statements. I believe I had it up here. Yeah, multiply quantified statements, right? So if you negate something like this, the first one, D for every always becomes a there exists, and there exists becomes a for every, right? And then you negate the thing, the statement, such that x plus y does not equal 1, because remember we negate this. I'll be uploading this whole PDF onto Piazza so you can look at it on your own as well. Alright, so that's negation. So now we could try this actually. There exists some let me get a different color. There exists some x in D, right? That for every y, x plus y does not equal 1. So for every y in E, right? Let's just say -2 equals y, right? There exists some x. So it doesn't have to be every x in D, just some x. So let's just say 0 equals x, right? Does -2 plus 0 equal 1? No. So that statement is true. And you'll find that if you try every other combination, if you keep going through all the elements in here, you'll find that this negation is actually true. So and since the negation is true, the original statement is false. That's called proof by counterexample, I believe. Or proof by contradiction, I think, is one of the two, where you disprove something by proving the negation of it. Right, so now on to B. And B says, x plus y equals negative y. I'll just put the set here again. Okay, so it says there exists some x and d such that for every y, x plus y equals negative y. So let's try this again, right? Let's say negative 2 equals y for now. Let's just get some random... Well, first let's see if this is even possible. Right, so x plus negative 2 equals 2, right? So now this means x minus 2 equals 2 plus 2 plus 2. X would need to be 4 for this statement to be true. There is no 4. 4 is not an element of D or E, right? So this is false. Let's move on to the negation. The negation would be what the... hold on. Let me take this. Shoot. Alright, so the negation of this would be for every x and d, there exists some y and e such that x plus y does not equal negative y. Alright, so now let's get some... This means for every x and d, right? So let's get some random... Let's say negative 2 equals x. And we'll get some random y. Right, we'll say y equals 0. Negative 2 plus 0 does not equal 2, right? So that's good for this trial. And you'll see that if you just continue throughout the whole set, this is actually true. So the... Whoa. Negation is true. So the statement is false. Alright. So yeah, that's your answer for that. So when you have a finite set like this, just use the method of exhaustion. To go through the set and see if what they're actually saying is true. And if it's not true, try the negation. Yeah, so we'll move on. It says to rewrite the statement in English without using this symbol for every word there exists or variables, and express your answer simply as possible. And also write the negation for that statement. So alright, let's see. So this says for every color there's some animal such that there's some animal A such that A is colored C. Right, so we'll say for every color for every color C, oh wait, no, I said without variables, right? Okay. For every color, there is some animal with that color. Alright. There's some animal with that color. That would be just the normal, just I guess rephrasing that in the formal manner. So the negation would be It would be there exists colors, some color C, such that for every animal A is colored C. So we'll write this out. No, this is actually negation. Is not colored C. So now we'll write this out. There exists some color C that every animal does not have that color. That'll be the negation of that. Alright, on to the next. For every book B, there exists a book B such that for every person P, P has read B. We'll say there is some book B that every person has read. The negation will be for every book there exists some person, people, where P has not read B. So I guess if you read this out directly, it says for every book there are some people who have not read that book. But you could just say there's some book that one sec. That every person has not read. One sec. I'm just gonna double check if that's the actual answer. Chapter 3.3. No, sorry, I said it wrong. There's no book that every person has read. I said it completely wrong. There's no book that every person has read. You could just say it like this, or if you wanted to, I guess you could say it how this what this really means, for in all books, for all books there are some people who have not read all books. Actually, no, this just sounds wrong. you should not say this actually. Even though that's basically what this means, to say this. Just think about what makes sense, I guess. Yeah. There is no book that all people have read. Alright, next question. It just says, for every odd integer n, there is some integer k such that n equals 2k plus 1. Alright, so we're supposed to just... Wait, I forgot to box this as well. Okay, so this says, for all integers n, there is some integer k such that n equals 2k plus 1. That's all, yeah. That's as simple as it can get, to be honest. I guess you could say, like, instead of such that, you could say where. But no, this is, that's essentially what that sentence means. For the negation, you could say there exists some odd integer n, where for all integers k, n does not equal 2k plus 1. Right, so we could say there is some odd integer n where for all integers k, n does not equal 2k plus 1. Yep. Alright, moving on. 18. Says for every number x, which is an element of the set of positive real numbers, there exists some element y in the set of positive real numbers such that y is greater than x. We'll say every positive real number x, there is some positive real number y such that y is greater than x. Wait, they said don't use variables, right? So, okay, from here you could just erase that. There's some integer such that one sec. No, wait, we can't use. I'm tripping. Never mind. We can use symbols. I'm tripping. Okay, so for every positive real number x, there's some positive real number y such that y is greater than x. Right? That's what that means. Alright, so the negation would be there exists some positive real number x such that for every y in the set of positive real numbers, y is less than or equal to x. Such that for every positive real number y is less than or equal to x. Remember, we're negating this, right? We have to negate that. Basically just flipping everything. Alright. Okay, here we have to use like universal modus ponens. So use a universal instantiation or universal modus ponens to fill in the valid conclusions for the arguments 2 through 4. And this is the universal modus ponens right here. It basically says if P then Q, and if we're given P, then we can successfully conclude Q. So let's look at this, right? If an integer n equals 2k and k is an integer, then n is even. So we can say this is P and this is Q. If an integer n equals 2k, and here it says 0 equals 2 times 0, then k is an integer. So, right, so this would be n equals 2 times k, and k is an integer. Right, I'm just describing what this sentence is basically saying, right? So, this is P. They've given us P, right? So from there we can use using universal modus ponens, 0 is even, right? Because we already said 0 is n equals 2k and k equals int. So 0 equals n. Yeah, so 0 is even. That is the conclusion we can draw because they gave us P. Now we're just telling them Q. Q is the conclusion. Alright, for all real numbers, A, B, C. One sec. For all real numbers, A, B, C, and D, if B is not equal to 0 and D is not equal to 0, then A divided by B plus C divided by D equals A times D plus B plus C. Sorry, A times D plus B times C divided by B times D. So they gave us all these numbers here, basically trying to show us that it's not 0. Are particular real numbers such that B is not equal to 0 and D is not equal to 0, right? So they basically gave us the first part again. This is P, if P then Q, this is P, this is Q, right? They gave us P, right? They're saying B is not equal to 0 and D is not equal to 0. Basically what we already said P is, right? They just gave us P, so now we're trying to tell them Q using universal MP. I'm just going to use MP as a shorthand way of modus ponens. I'll say A times B, A divided by B plus C divided by D equals AD plus BC divided by BD. That's it. We don't need to substitute in the numbers or anything. We'll just say that. I mean, you could put in the numbers if you want to, but actually, yeah, let's put in the numbers. Might as well. It's better to be safe. So A is 2, right? Well, A is 2, and B is shit. A is 2, B is 3 plus 4 over 5 equals 2 times 5 plus 3 times 4 divided by 3 times 5. Just leave like that. Yeah, that's correct. Okay, so we have all irrational numbers are real numbers. Even though it doesn't explicitly say if P then Q, it's essentially in that format, right? They've given us P, and we have Q, right? So we'll just say P then Q. I mean, even though they don't explicitly say if then, you could just think of it like if a number is irrational, then it's a real number. Like, they don't have to explicitly tell you if then, right? If you can write it into if then it is if then, right? So this is P then Q. They give us not Q. So from not Q, we would have not P. If you remember, that's the tollens. That's the modus tollens. Whoa, where did I put it? Here. That's modus tollens. P then Q, not P. And we could use that as a conclusion for not P. That's the contrapositive, if you remember. But yeah. So we'll just say if this is P, this is Q, and they've given us not Q, we'll say 1 divided by 0 is not irrational, right? Because it's not a real number, so it must not be irrational. If P then Q, and they give us not Q, then the conclusion is only not P. Using universal and P. And MT, tolerance. On to the next. Okay. Some of the arguments are valid by modus ponens or modus tollens. Other are invalid and can exhibit the converse or inverse error. State which are valid or invalid, and justify your answers. Okay. All healthy people eat an apple a day. Just as before, we could just turn this into P if P then Q, even though it doesn't explicitly say if P then Q. This is P, this is Q. Right, eat an apple a day. It says they've given us Q, eats an apple a day, what we said is Q. Then they just say P as the conclusion. If you look here, this follows the converse error. They give us P then Q, they tell us Q, but then they conclude with P. That's not correct. Like, somebody, I don't even know, like, you don't have to eat an apple a day. Just because you eat an apple a day doesn't mean you're healthy. Like, I don't know. Yeah, it just doesn't make sense. So we'll just say this is invalid by converse error. Alright, yeah, on to next. All freshmen must take writing. Just like before, P then Q. This is P. This is Q. Caroline is a freshman. They've given us P. Caroline must take writing. They've given us Q. This follows modus ponens, right? They've given us P and they conclude Q. So this is correct. Okay, on to the next. All healthy people eat an apple a day. This again. P, then Q, P, then Q. Herbert is not healthy, right? So they've given us not P. So Herbert does not eat an apple a day. They've given us not Q. If you look up here, this follows the inverse error. If P then Q, you give me not P, then conclude not Q, which is not always the case. So we'll say this is invalid through the inverse error. Alright, next. If a product of two numbers is 0, then at least one of the numbers is 0. Right, so if this explicitly says P then Q. So they say, for some particular number x, neither 2x plus 1 nor x minus 7 equals 0. So they tell us not Q. Neither of these is 0. You told me at least one of them would be 0, right? But neither of these is 0. So that's the negation of Q. Then they say the product of these two terms is not 0. So that's negation P. So if you recall, this is modus tollens. I'll go back up. Yeah, modus tollens. Not if P then Q, you say not P. Not Q, and then you can conclude not P. Okay, next. If a number is even, then twice that number is even. P, then Q. The number 2n is even for a particular n, number n. So they've given us Q. The number n is even. They've given us P. So this follows the converse error. If P then Q, you tell me Q, then conclude P, which is not necessarily always true. So this is invalid. Yeah. Alright, next. Alright, it's telling us to rewrite the statement, no good cars are cheap, in the form, for every x, if P of x then not Q of x, and indicate which of the following arguments is valid or invalid, right? So let's just rewrite this first. No good cars are cheap. This says for every car, let's just say for every car x, if x is cheap, we'll say cheap is if c of x, or c of x is cheap, then if it's cheap, then it's not good, basically. That's what this sentence is saying, right? So we'll say g of x is good, but if it's cheap, then it's not good, right? It says no good cars are cheap. So if our car is not cheap, then it's not good. I mean, if our car is cheap, then it's not good. Yeah. So that's what that means. But that's not the answer there. Not yet. So now we need to see if this argument is valid or invalid, right? So it says a rimbaud is a good car, right? So we said if it's cheap, then not good. So we have good, and it says not cheap. So actually, wait, to make this clearer, we could just say this is P, then this is Q. So a rimbaud is a good car, that means not Q. A rimbaud is not cheap, that means not P, right? So we could see that this follows modus tollens. Right, so yeah, that follows modus. Wait, I had this backwards. I wrote this sentence, the whole thing backwards. Yeah, my bad. I'm supposed to say if a car is good, if g of x, if the car is good, then it's not cheap. Alright, because that follows the order in which this sentence is. My bad. So from here we could say this is P, this is Q. So a rimbaud is a good car, so that's P. A rimbaud is not cheap, that's Q. So this follows valid by modus ponens. My bad, yeah, that was completely my fault. I just wrote that whole sentence wrong. That just gave me a completely different answer, but you want to follow the order in which the sentence actually goes. So no good car is cheap, right? So we'll say if a car is good, then it's not cheap. We'll say good first before cheap. And then from there we could say good is P and then not cheap is Q. From there we could follow it with this and see if the conclusion is correct or not. And we found that it's valid through modus ponens. Okay, next question. We're going to have to use a bunch of diagrams for this. So, all teachers occasionally make mistakes. No gods ever make mistakes. So, no teachers are gods. Right? So, we'll do this. It says we'll go one by one. All teachers occasionally make mistakes. So, what's the overarching thing? Making mistakes. And teachers is nested within it. Teachers is nested within this overarching circle of making mistakes. It's not the other way around, that mistakes is nested within teachers. That would mean that only teachers make mistakes, like no other anything makes mistakes, right? That's limited only to teachers. But no, teachers are included within this overarching circle of mistakes. We'll go to the next one. It says no gods ever make mistakes, right? So we'll take this again. No gods ever make mistakes. So gods is out here. It's out of the circle. It's not in mistakes at all. So then from here it says no teachers are gods. Well, of course that's true. The teacher circle is not within the God circle, right? So that would mean no teachers are gods. So since they're not, since teachers are not within the circle for gods, we can see that they're independent, and that the statement is true. This picture alone should be like enough, but you want to put like a sentence describing what the picture actually means, you know? Yeah. Alright, next. No college cafeteria food is good, and no good food is wasted. So no college cafeteria food is wasted. So let's start from the first. No college cafeteria food is good. So good, the circles for good and college cafe food are separate. They're independent of each other. One is not within the other. They're independent. No college food is good. So they're just independent circles, right? Next. No good food is wasted. What does that mean? That means you have good food. You have college cafe food. And all we know is that wasted is not within good, right? We're not given any other information. All we know is that all good food is not wasted. So these two circles are independent of each other. But what we don't know is that these two circles are independent of each other. So this is one case. That can happen, right? That's one scenario. But it could also be this case. There could be good food, college cafe food, and wasted could intersect. Wasted could be like this. Wasted could be like this. Or wasted could be like this. We don't know. What this whole diagram is what all these diagrams are to present is that we don't know what's going on here. This could be a little messy, my bad. But all that to say, we don't know. We don't know what the scenario is. All we know is that good food and wasted food are not related. But what we don't know is the relationship between what in the world? What we don't know, what we can't determine is the relationship between college cafeteria food and wasted. You just saw all these possibilities I listed out, right? So from these diagrams, we can see that we cannot determine the conclusion from the premises. This conclusion is only true like some of the time. We can't fully say hands down that no college cafeteria food is wasted. We don't know. It's not something that we can determine for sure. Therefore, it's wrong. It's invalid. Alright, you should say this is invalid. So, this statement is invalid. Alright, so yeah, that's how you do those kind of things. So these diagrams can be pretty helpful at times, like let you see if the conclusion follows from the premises or not. So yeah, that's all the questions we're gonna do for today. If you have any more answers, I know I couldn't make recitation today, so I had to do this video. It's not really the same because like no one can ask me questions or anything. But if anyone were to have questions about the stuff that we covered today, or anything like on the homework or anything, alright, just email me, shoot me an email, or come to my office hours. But yeah, that's it for today.